get started because sometimes it's necessary. I've met some of you during the orientation, but I would like to just introduce myself again in case you didn't go there and ignore my email. So my name is Bufan. I'm your Wednesday lecturer. I went to Vassar College for undergrad and Cornell for my master's in science, and I'm currently at the University of Rochester doing a PhD in physical and organic chemistry. And that's me. So I want to talk about some expectations that I have for y'all. First of all, I encourage all of you to leave your cameras on and your audio on if you can. I understand that some people might have technical difficulties, and that's okay if you have to leave or turn your camera and audio off. Also, I encourage you to interrupt me during my lecture with questions, concerns, and comments, such as, you're going way too fast, or I think you're absolutely wrong. Stuff like that, because, having done so many years in graduate school, I am in constant self-doubt, and I will think twice and have a good discussion with you if you think my teaching is incorrect. And, see, I have a whole list of things I want to talk to you about before I even get started with the lecture. So I'm mostly going to divide my lectures into two parts. One part with slides, the other part with drawing on the very little whiteboard that I have. And when I start drawing, I'm hoping that you can draw with me as I talk, because, well, I understand that those videos are going to be posted online, but I think it will benefit you if you do it as I do it, because you can then ask me questions if you don't understand what I'm talking about. And then the last thing is that I recommend that you read the textbook after the lecture, and it's entirely up to you. My job here is to make your life as not painful as possible when you go through organic chemistry, and we're not here to judge how good of a reader you are, so it's entirely up to you. It's just nice to read through the text after learning about all this new material so that you will solidify your memory a little bit. So that's all my expectations. Any questions regarding what I just said? You guys are quiet. Okay, I'm gonna get you start talking at some point, and I like the challenge. You guys are all very quiet. Okay, so a bunch of random things that I would also like to bring up. So my office hours are on Thursdays. I don't remember what time, but I'll be there.
It was 2:30 to 4.
Okay, thank you, Ashley. See, people like Ashley constantly reminding me of stuff that I forget. So from 2:30 to 4, I will be there. You're more than welcome to come see me, asking me about chemistry or grad school or how it feels to be a researcher in a real lab. It doesn't really matter. If you just want to see my cats, you're more than welcome to show up, and I will show up. Okay, so another thing is I might accidentally swear during lectures, and I apologize in advance if that happens. I know that might make some of you uncomfortable, so please let me know if that really bothers you, and I will try my very best to not do it during lecture. It's just I work in an environment where everybody swears. My boss swears, and we swear during our group meetings as well. So it's really hard for me to just not swear. It's great when I talk to my parents because they're Chinese, they don't speak any English at all, and I just swear in English all the time when I talk, but they don't. Anyway, so third, my cats might show up during lecture. I will try to keep them away, but sometimes they jump onto my desk and they put their face against mine for attention. So if they show up, please excuse them. I will make sure that they get out of your sight as soon as they approach. Okay, so the last thing is, please feel free to email me, send me messages anytime. You can do it during the lecture, you can do it after the lecture, it doesn't really matter. I check my emails very obsessively, all the time, more than I check my text messages. So I will respond as soon as I see your questions. All right, so that's all I have for the ramble. But Projections into skeletal structures that you just learned this Monday. So, first thing, let's talk about hydrocarbons a little bit. You don't have to take notes because we're going to post the slides online, so you can just listen. Right now, I'm not drawing anything on the whiteboard. I just want you to pay attention to me. So hydrocarbons, they exist everywhere in our lives. And first of all, alkane. They're also called paraffin. And the signature of alkanes is that they're made of just carbon-carbon single bonds. And for short-chain alkanes, they're mostly just gas. For example, methane, ethane, propane, and when you get to butane, things get a little weird. They become longer chains, and they can start liquefying or solidifying. So for longer chain alkanes, you might encounter liquid or a solid, depending on how long the chains are exactly. And some examples for alkanes, well, we can find them in a lot of fuel sources, such as natural gas and petroleum. I don't know if you've read about the industrial process of separating natural gas from petroleum from other fuel sources. If you're interested, you can just Google, look at YouTube. There are a lot of cool videos about that. Basically, we separate them based on their boiling points, which I will get to in a couple minutes. So, let's move on to alkene. We're not going to focus on this, just want you to know that there are 3 types of hydrocarbons. So alkene, they're also called olefin. Old people, old school chemists call them olefin, and they are made of carbon-carbon double bonds. And alkene themselves are not very useful if you just pick them up. Unlike alkanes, if you have a bunch of propane, you can light a torch, or butane, you can light a torch. But with alkene, we typically don't do that. What we can do, however, is to take alkene and turn them into other things, such as polymers or feel-good products, such as candles, the scent that you get from lemonade, for example. That's a very good smell, and you can put them in shampoo, put them in food, whatever. And last but definitely not least, pharmaceuticals. And this has something to do with the unsaturation of the bond. So, what does saturation mean? Think about it this way. So we all know the carbon forms 4 bonds. It does not exceed the octet rule. So if one day you drew a carbon with 5 bonds, you gotta be very careful. You must have made a mistake somewhere. So saturation means that your carbon has 4 things attached to it. Simple as that. Doesn't matter if those things are carbons, hydrogens, halogens, like chloride, fluoride, bromide, stuff like that. As long as it has 4 things attached to it in the entire molecule, it's saturated. However, with unsaturated, you're going to have your carbon attached to 2 different things, or even 1 thing. That means unsaturation. And for unsaturated carbons, a lot of reactions could potentially happen because you have these pi electrons to push around. And we'll get more into that when we talk about reaction mechanisms in just a few weeks. So right now, you just need to know that saturated carbons do not want to react, whereas unsaturated carbons would love to react with all kinds of things. So, last but not least, alkyne. They are made of triple bonds. And I was not able to find the sign of a triple bond, so I didn't put it there. But you get the idea. They're also used for polymerization and synthesis of pharmaceuticals, etc. You can just look up examples online. I was lazy, so I didn't look up anything. But they shouldn't be very hard to find. So, as I threatened to do earlier, we're going to take a look at the trends with different alkanes. So let's talk about alkane nomenclature first, because it's very straightforward. I bet you all heard of methane, ethane, propane, butane. And basically, all the alkanes have the, what do you call it? Suffix? Is that the word for that? Like the stuff that you put in the end for something? Anyway, all of them are called something expose yourselves to this at the moment so that when you see something ane, you know that it's definitely an alkane and it's saturated. So let's talk about their melting points. What do you notice when you look at their melting points? Somebody's going to say something, otherwise I'm just going to sit here and wait. Somebody say something, please.
Well, for like the first, for the first three, I remember they would decrease, but then after that, they would just start to increase.
Yeah, you're absolutely right. So the overall trend is, well, thank you for answering, by the way. And your name is
Nestor.
Your name is Nestor. It's good to meet you, Nestor. This is how I learn your names. You know, like if you don't talk to me, I will never learn your name, and I hate that. I want to know your names. Okay, so as Nestor just said, the melting points generally would go up as we have longer chains. And I wonder why. What does it mean to have a higher melting point? Does it melt easily or does it melt very not easily? Somebody else, please.
Not easily.
Not easily, right? Thank you. How do you pronounce your name?
Bintu.
Bintu. It's nice to meet you, Bintu. So stuff starts to solidify. And basically, you cannot hold dodec in your hand. I've worked with dodec and it's a very sticky liquid. But when you get to, how do you pronounce this word? Icosane? However it's pronounced. You can hold it in your hand and its melting point is 36.8, so slightly below your body temperature. So, somebody raised their hand. How do I guess I can just ask, what's your question?
I have a question. So I'm just thinking, the negative boiling point to have density, is there a specific reason why?
That's a very good question. So methane, ethane, propane, and butane, they are gases. And all the gases are very light. So we typically don't measure the weight of the gas unless we compress them together to make a gas cylinder. So typically, how do we store these gases is that we compress them and make them liquefy, and then we can measure their densities. So at room temperature, we do not measure the densities because they're just gas. You can't feel it. So that's the reason why we don't have densities here. But we do measure the density of liquefied methane, ethane, propane, butane. Does that answer your question?
Yes, thank you.
Okay, you're welcome. Let's keep going. So we talked about melting point. I'm sorry?
You said the first four are gases, but what about the rest? They're not gases.
The rest, so you can, let's see, pentane, hexane, heptane, these are liquids at room temperature. You can look at the melting point. That's what we're getting at right now. For pentane, the melting point is 36.1 degrees, which means that it turns from solid to liquid at 36.1 degrees. Okay. So in a chemistry lab, we store pentane in little bottles, and they're just very nice liquidy things. They're colorless and they smell weird, so I do not suggest huffing pentane when you encounter it, just because it's so easily vaporized and it doesn't smell good. And you will probably pass out after huffing it. But that's the reason why we have densities for those, but not for the gaseous ones. Okay, so boiling point. We just talked a little bit about boiling point. What it means is that something turns from something turns from liquid to gas at that temperature. So as we go to longer chains, the boiling point will increase, which means that it doesn't turn to gas that easily. So what's the force that's forcing it to not turn into gas so easily? You learned this in Jenkin. Let's see who remembers that.
I
Yes,
think
Nestor.
I'm a guess. Could I have London dispersion?
Yes, you're absolutely right. Thank you.
Oh my gosh, it was a gut thing. It was a gut thing. I was like,
Yeah, it was a gut thing, right? You have a pretty good intuition about it. So, yes, London dispersion force. We all know the molecules are not rigid. They're electron clouds. Probabilities. And when you have those long chain hydrocarbons, your electron clouds are going to get stuck to each other. You're going to get partial polarization, and they would stack so that there's more interaction between molecules, and it's going to be harder for you to rip them apart, because for liquid, they're closer to each other, and for solid, they're even more close to each other. So that's the reason why we see these kind of trends in melting point and boiling point. Okay. So any questions regarding the trends and the naming of simple alkanes? If not, I'm just going to move on to the next slide. So nomenclature. We just talked about the nomenclature for unbranched alkanes. For branched alkanes, I made a separate PowerPoint document for you. Basically, I took pictures out of the textbook if you don't like looking at the textbook, but they're basically the same thing. And I encourage you to learn it on your own, because you're having an exam on this Friday. You know, you might want to get prepared for that. You won't be asked to name anything complicated, just branched alkanes. Make sure you learn how to name them. Okay, so we're done with our first topic. Sorry, did somebody want to ask a question?
Yeah, I missed what you said. Where will you see the branched one?
The branched one. I will upload some slides onto the Canvas after this class. So you can go there and just look at the PowerPoint and go through each slide. I think I have 10 slides because there are 10 rules for it. But they're very straightforward. And if you have any questions at all, you can just go to office hours or come talk to me tomorrow, and we can go through them together. Okay? Cool.
Are we supposed to memorize these? The rules?
The rules, they grow on you. Let me say that, they grow on you. So initially, you're going to have a little trouble maybe memorize all the rules, but they grow on you. As you see more molecules, your answer would come out more spontaneously. And let me just tell you the truth. Nomenclature doesn't matter at all. You're going to have to learn it because you just have to learn it. I think it's a flaw in the chemical education system. They're absolutely useless. And I got to tell you that I don't remember 80% of the nomenclature rules, and it does not affect my research at all. So it's just something you have to memorize. Therefore, we're not talking about this in class because we have more interesting and useful stuff to talk about. And I believe for exams, it's okay for you to look at course materials, right, Ashley? I'm not sure.
What were your questions?
Oh, so for the exam, they can look at textbooks or course materials to help them, right?
Yeah, it's open book. You guys can do whatever you want.
Yeah, so wonderful. So there's no need for you to memorize the rules for now. But
yeah, just to point out, they do test nomenclature on the exams. So like while Bufan said it's like not important per se in chemistry, but in the exam it does show up, just so you guys know.
Yes. I'm not saying that you shouldn't learn it. You should learn it because it will appear in your exam. But that's the only reason why you should learn it, at least from my point of view. Anyway, let's move on. So we're done with our first topic. And next, we're going to go into functional groups. I'm going to show you a picture. Don't get scared when you see it. Sorry, I'm receiving emails from people. Not important. You're the most important thing to me right now. Okay, so there are a lot of functional groups in organic chemistry. And eventually, I'm saying eventually, not right now, you will have to memorize all of their names and what they look like. And when I say, draw me an aldehyde, you will draw exactly what an aldehyde is. But right now, just look at these pictures and know that there are different functional groups. And that's it. Because during an exam, you will be able to just come back to the slides or go to your textbook to find their names. But it's good that you're exposed to them now. You'll have much more time to spend with them so that you won't have to, stress out for the actual course. So these are all the functional groups that I encourage you to look at after class. Next, we're going to do some activities. That's fun. We're going to try to identify functional groups in a bunch of molecules. So the first molecule I want to show you is lysergic acid diethylamine. So that's the acid, the street drug. So I want to show you these molecules because they're actually not structurally complicated, yet they're so powerful when you ingest them. You will hallucinate sometimes and potentially feel like you enter a different dimension. But, if you see the structures of these molecules, they're really not that complicated. So just follow my cursor. Here we have an amide. What does that even mean? Well, we notice that there's a nitrogen with some alkyl groups attached to it. And here we have an oxygen double bonded to a carbon. So if you see something like this, oxygen, double bonded carbon, right next to a nitrogen, that is an amide. That's the name we give them. Okay, so let's move on to amine. If you see a nitrogen single bonded to 3 different things, and those things could be hydrogen or just simple alkyl groups. If you see those things, they're amines. And the last one, but definitely not the least important, you will see those in a lot of psychoactive drugs as well as just drugs that we use to treat illnesses. So here's an indole. What does that mean? Well, it's one phenyl ring attached to a 5-member ring with a double bond, and also there's an NH. So don't worry if everything that I say right now sounds like a different language. This is just to expose you to different functional groups. Again, we don't expect you to memorize them today or tomorrow or next week, just to show you what they are. So lysergic acid diethylamide was first synthesized by Albert Hofmann in 1938, and back then we didn't have all the rules that we need to follow in chemistry labs, such as you cannot eat what you make, you cannot huff what you make, don't take stuff home after you make them. So back then, after Albert Hofmann synthesized this molecule, he basically just ate it and had a 12-hour trip straight. And it was fun for him, I bet, and he made a lot of money off of this. So it works because it's structurally similar to serotonin, which is a neurotransmitter. And we can examine the structure of serotonin. It's not complicated at all. So we see this amine, which is very similar to this that we just looked at. And we see this indole moiety. And also there's an alcohol. When we talk about alcohol, we always think about ethanol. But alcohol is not just ethanol. It's basically everybody with an OH group attached to it. And I know that sometimes you will be tempted to say, oh, hydroxide, that's what we have here, right? It is hydroxide, but in organic chemistry, we call it alcohol. So you gotta make the transition here. Any questions regarding the acid or any functional groups that I just introduced?
Why do the 2 amine groups look different?
They look different, yes. I'm glad you caught it. So to be an amine, you don't have to have everything be an alkyl group. You can have hydrogens or alkyls. As long as you have hydrogens or alkyls and there are 3 of them around a nitrogen, it's an amine. Did I answer your question? Cool. Any other questions? Feel free to interrupt me during the lecture. I love that. If I'm going too fast, too slow, too nonsensical, just let me know. Okay, so next.
Oh, I have a question.
Yeah.
So for the first one, for the lysergic acid, so those 2 hexagons, they're just nothing. Like they don't really have a name, I guess.
We don't. Well, I guess for this hexagon on top, you can call this a cyclic alkene because it's cyclic, right? It's a ring, and there's an alkene in there. But for the other hexagon, it's just a hexagon. We don't have names for these. But, as you learn about different functional groups, they will grow on you, and you will be able to recognize whether or not that's a functional group. So don't worry too much about that yet.
Okay.
But I'm glad you raised that question because we have to be aware that molecules can contain functional groups, but not everything in a molecule is a functional group. Cool? All right. Breaking Bad. This show got me through organic chemistry when I was as young as you are now. And how many of you have seen this show? Very many? Somebody raise their hand. Well, okay, cool. I will assume that many people have heard of it at least, and it's a show about methamphetamine. And the name of the compound gives it away that this molecule is an amine. So let's look at this part of the molecule right now. It's an H. There's a methyl group, and right here there's a huge chunk of alkyl attached to the nitrogen center. Therefore, it's an amine. It doesn't have to be all alkyl groups. As long as there are three things and they're either alkyl or hydrogen, this is an amine. And here we have an arring, which basically it's an aromatic ring. You will learn about aromaticity in the future, so don't worry if you don't understand what aromaticity means right now. All you need to know is that if you see something that's cyclic and with double bonds alternating, that's an arring. And so one interesting thing about methamphetamine, I actually looked this up, and I'm probably on the FBI's watch list right now because I looked up the total synthesis recipes for methamphetamine when I was learning synthetic chemistry. And I'm a synthetic chemist, which means that I make things. And sometimes I'm just very curious. I want to look up different things and see if I'm able to make them. And meth is something that I think I will be able to make given all the starting material. And I'm telling you this now because I think from a scientific standpoint, you should feel comfortable looking at all kinds of molecules and trying to read through the synthesis and see if you understand it. At least for me, what helped me memorize all the different kinds of reaction was just looking at weird molecules and looking at their synthesis. So methamphetamine is a very simple molecule that you can potentially start with. And here there are two different synthetic routes. Not saying you should try it at home. I don't advise that. That reflects my personal opinion, not the opinions of all the TAs of Cornell University. But since I'm not affiliated to Cornell anymore, I can say whatever the hell I want. So, standard synthesis, that's also called the pseudo method. You take cold medicine and do one extraction. You take out this organic molecule. You will learn about how to do extraction in your chemistry lab, I believe. So you take out this molecule, which also looks very simple, and you do a reduction, and then you get methamphetamine. One interesting thing about methamphetamine is that there are two-handedness. Like the two molecules, they look exactly the same, but they're mirror images of each other. So, I don't remember if it's the left-handed version or I think it's the left-handed version. It's methamphetamine. It's a street drug. Whereas the right-handed version, you find it in your cold medicine. So that's why when you get Sudafed, you have to get doctor's signature because that's basically what this is. But you're not experiencing any psychoactive effects because it's the wrong-handedness. So that's called stereochemistry, which you will learn about, I think, from me in just a week from now. So I'm going to save the story for later. And bleed mass synthesis, just for entertainment. I'm not going to go into details. So here's a list of all kinds of drugs that you can look at, and I want you to exercise on your own, see how many functional groups you can identify from all of them. And notice that amine is a very common functional group in a lot of drugs, not just for psychoactive drugs, but also for drugs that we use to cure illnesses. Book recommendations, Pickel and Fickel. So the authors, Alexander Shulkin and Anna Shulkin, were a couple, and they did a lot of experiments with themselves. And there are very many recipes for how to make very interesting molecules in the back of the book. And sometimes when I feel stressed and anxious, I would just go to the recipe book and read pages after pages of chemistry formula, and that's very soothing for me. And you can call me a weirdo, but if one of you or several of you become chemists in the future, you will know exactly what I mean by that. Keep that in mind. Okay, so we're done with half of our material, but the most important thing we haven't discussed yet. That is 3D drawing of hydrocarbons and Newman projection. And now I'm going to stop sharing and start drawing on my whiteboard. Okay, so let me flip my camera so that you'll actually be able to see what's on my board instead of having it backwards. Okay, there we are. I know that you learned how to draw skeleton structures and 3D structures in the past, but we're just going to do a review, and I want you to take out your pen and pencil and draw with me. So, let's start with the most simplest molecule of organic chemistry, that is methane. So how do I draw a methane? Well, okay, so I'm going to draw a 2D picture first, and if you know what it looks like, still draw it though, because you can refer back to it and see what we talked about. Carbon, hydrogen, hydrogen, another hydrogen, and in the end, have this. That's my methane. Can you all see it, or should I move closer? Anybody have trouble seeing what I have? Okay, cool. I'm just going to assume that you all can see this. So, a 3D structure of methane. Organic chemistry is very simple, as in that everybody has 4 bonds, mostly, or less than 4 bonds. So you don't have to remember all the crazy geometries for molecules that have very many bonds. So for a saturated carbon, what's the local geometry? Somebody other than Nestor talk to me. What's the local geometry for it? Thank you, Destiny. It's tetrahedron, right? So we're going to just draw a tetrahedral methane. And if you know exactly what it looks like, just don't look at my board and draw it on your own. And then we can compare our answers. So we have a carbon, have an H, have an H. One of them goes into the board, the other one comes out of the board. Just so everybody's clear, when I draw a dashed bond, it means that the atom goes into the board. When I draw a linked bond, it means that the atom comes out towards me. So we have 2 in playing, and 1 goes in and 1 comes out. That's the simplest organic molecule that we can draw. So we're halfway done with the review. Now I'm just going to draw a little bit more complicated molecule, which is ethane. And we're going to use that as an example for drawing Newman projections, so pay extra attention, make sure you draw this right. So I'm going to draw a 2D structure of ethane, sorry. H, filling all my H's. All right, so how do I draw the 3D structure for an ethane? What's the logo geometry?
You keep you should keep both the C's on the same plane, and then both of them are tetrahedral. So
that's a great idea. I like that. Okay, so let me do what you just said. I'm going to keep the 2 carbons where they are. And what am I going to do next? Somebody else?
Sorry.
No, it's okay.
You can create like a tetrahedron with the 2 carbons.
Yes. Okay, draw tetrahedrons of 2 carbons. So I'm just going to keep my 2 H's in place. And then I'm going to draw, sorry, that's a flat picture. So I'm going to draw a tetrahedron coming out, and I have an H going in, and an H coming out. So that would be a 3D drawing of an ethane molecule. And so draw that down in your notebook or a piece of paper. because we're going to come back to it in just a few minutes. So I think you're ready to learn Newman projection. If you have any questions, you can ask now, because then we're going to move on to something completely different.
I can't see the corner of the board.
Sorry?
I
Corner
can't see
of
the
the board?
board. Yeah.
Oh, sorry. Can you see it now?
Yeah, the light was kind of on the way, but I can see.
Yeah, I'm sorry. I have no shades for this window that's right in front of me. So I can turn my computer so that you can see it clearly, but I would try not to draw in that area.
I have a quick question about the drawing. Like, if you drew that on a test, would that be like correct? Because like the C's are linear, and it's supposed to be like they're supposed to be like a tetrahedral. So, like, if I drew that on the test, would I be marked wrong, or is that okay?
So to answer your question, I'm glad you brought that up, because there are multiple ways of drawing a 3D structure for the ethane molecule, and I chose the easiest way, which is, let's look at the local geometry of the ethane, right? So you mentioned tetrahedra. So let's look at the first carbon. Is this carbon a tetrahedron? We have one in plane, number 2 in plane, one goes in, one comes out. So is that a tetrahedron?
Yeah.
That is a tetrahedron, right? So let's remember that. That's a tetrahedron. What about the second carbon?
Yeah.
That's also a tetrahedron. So we have a bond that connects both tetrahedrons. Basically, you have 2 tetrahedrons back to back. So this is the easiest way for you to draw it. But you can also draw it, I guess.
No, it's okay. I was just wondering if like that would be right on a test, but like I understand now.
Yeah. Good. Let's just pay attention to local geometry. I know the ethane's not going to look like one giant tetrahedron because there are 2 central atoms. So just remember that and you'll be good. Okay?
Okay, thank you.
You're welcome. Okay, so sounds like you're all ready to learn Newman projection. And before we learn Newman projection, as I'm erasing the board, I want y'all to do one thing, which is very simple. Visualize a 4-legged furry animal. 4-legged furry animal. Doesn't matter what it is. If you're a cat person, think about cats. If you're a dog person, think about dogs. If you like wolves, other furry animals like foxes, whatever. Just visualize an animal. Think that it's walking towards you. So think about the front view and think about the side view. So I want you to think about that for half a minute. Just do your best to visualize the animal. I'm a cat person, as I've made it very clear in the past. So I'm going to just draw a cat on my board. I think it's very important that you be able to visualize Newman projections, and I think the easiest way for us to do this is to start with something familiar. That's the reason why I asked you to visualize a 4-legged animal, because we all see them. So for me, I visualize the cat. I'm going to draw it on the board. And please excuse my drawing. I'm not an artist. It's going to suck, but bear with me. So I have a kitty. That's kitty's head, ears, kitty's neck, my matchstick kitty. So I want to draw the kitty in 3D. Therefore, I'm going to draw one leg going in, other coming out, one leg going in, other coming out. And I want to give my kitty different colored socks. So for the legs that are going in, my kitty is going to have blue socks. And for the legs that are coming out, I'm going to give them red socks. So this is the side 3D view of my kitty. What I want you to do right now is whatever furry animal you were thinking of. Draw its front view as if we were looking at it, him, her, them, pick your word, and visualize what the animal would look like if we look at the animal from the front, if we look down this way. So think about it and then try to draw it on your own and see what you come up with. It's okay. There are no wrong answers. I believe in your imagination. I want you to do it first so that you have an idea of how to visualize it in 3D. Then I'm going to draw what I think is a good representation of what the cat looks like from the front. It's still going to be a matchstick cat. Okay, so I'm going to draw my answer. I'm going to say front. That's my front view of the kitty. I have a cat face. This is my cat's body, which is another circle. And I'm drawing the kitty's legs. And there's the kitty's tail. Everybody see it? Okay, so here I have a question. My kitty has different colored socks. How do I color the kitty's feet in this picture? Let's start with the right-hand side. What color do I put on the right side of the kitty? Somebody new, please talk to me. I want to learn your name.
Would it be red color?
It would be, sorry, what color?
Red.
Would it be red? I agree with you completely. We're looking at the kitty this way, therefore the red socks are going to end up on the right-hand side. So that's how I'm going to color the kitty. Thank you very much for your answer. What's your name?
My name's Lizette.
I'm going to, let me, Lizette?
Yes.
Nice to meet you, Lizette. Okay, so since she gave me the answer for the right-hand side, I'm going to color the other side all blue. Because there are only two colors. Any questions regarding how I colored the kitty or how I drew it? Okay, so I will assume that everybody is following me right now. So what about a rear view of the kitty? Say if I look at the kitty from the back. I want you to draw the picture on your own and then look up to see what I just drew. So, rear view. I'm going to draw the kitty's head and draw the kitty's body. There's a tail, head, two more legs. Feel free to look up once you're done. There's no rush. Okay, so how do I color the kitty's socks in this picture?
Well, now they would be switched, so like red would be on the left and blue on the right side.
Thank you, Priya. That is awesome. So the kitty is now switched. Right would be on the left, whereas the other one will be on the right. So right now we have mirror images. They're mirror images of each other, and you will learn about this in the future in more details about stereochemistry. But now just know that when you look at the kitty from the rear view, the socks are going to end up on a different side. So I think now you're ready to draw actual Newman projections. Well, actually, we just drew the Newman projections for the kitty. So what about the Newman projections for an actual molecule? Let's go back to ethane, which is what we just practiced on. So let's just compare the ethane to the kitty. I say they're the exact same thing. If you don't believe me, let's draw them, and you will see exactly why I said they're the same thing. So, draw my 3D ethane, and you need to draw this on your own, too. Draw the 3D ethane. I have my H, one goes in, one comes out, one comes out, one goes in. You done drawing your ethane? Okay, cool. So, I want you to draw the Newman projections for the ethane molecule. See how it is? It's just the exact same picture as the kitty, aside from the head and the little tail. So you've actually learned how to draw the Newman projections already. So let's start from the front. I want you to draw the front picture of the ethane molecule. So I'm going to draw my answer, and you can compare yours to mine.
There's light stuff, like you can see.
I'm sorry?
If there's a light that's like covered.
Right, I see. Better?
Yeah.
Wait, so a molecule still has a body, like a circle body?
I'm glad you brought it up. So that is when we look down at this bond. See right here? Do you see that?
Yeah.
So right here we have what atom?
The carbon.
We have a carbon. So, in a classic view of chemistry, every atom is just a sphere. So when we look down that bond, all we see in the center is just a round carbon atom. Right. And there's another carbon behind it, but we don't draw it because we're looking directly at the carbon-carbon bond. Therefore, we can't see the second circle.
Thank you.
Okay.
Can you adjust your camera so I can see the? I actually can't see the.
Oh yes.
Okay, thank you.
Does the orientation of like the wedge and the dash hydrogens, does that matter for stability?
Sorry, can you repeat your question?
Can you hear me?
Yes, I can hear you now.
Does the orientation of the wedge and dash hydrogens, does that matter for stability?
We actually will talk about stability in just a couple of minutes. So you will see what actually matters. To answer your question directly, I don't think that's the case, but you will learn about what actually matters in just a few seconds.
You didn't show like which one was going out or which one was going in for the front.
Sorry?
Like which leg is going like out, which one is a wedge, which one is going in.
Right, so that's why I had the kitty wear different colored socks. We can do that for the hydrogens too. So for the hydrogens that are going out, I'm going to circle them with red. For the hydrogens that are going in, I'm going to circle them with blue. So, let me ask you, if I'm looking from the front, what color are my hydrogens on the right?
Red.
Red, right? You're absolutely correct. So, this is blue. So I'm going to have red hydrogens on this side. And then I'm going to have blue hydrogens on this side. What if I looked at it from behind? What if I looked at it this way?
It's just going to be switched.
It's just going to be flipped, right? So wedge and dash bonds will manifest themselves this way. But in this case, because both carbon center has 3 hydrogens, it doesn't really matter. It's completely symmetrical. So, it really doesn't matter. But it matters when you start having different substituents. By a substituent, I mean a thing. For example, if I don't like hydrogen. I'm going to put a chlorine up here. Now all of a sudden there's something that's different. And you can't randomly put the chlorine anywhere. So which hydrogen should I erase in order to put the chlorine on it?
The first blue one, the front one.
The first blue one, right? You're absolutely correct. Thank you. So we can't put the chlorine in the back because it's on the front carbon. We can't change it to a red one because it's going inside. So that's stuff you have to pay attention to once you have asymmetric molecules. But for ethane, we don't have to worry about those. Make sense?
I have a question.
Yes.
So yesterday we learned about further rotation. So technically the carbon that's behind the first carbon can free rotate, so then how can you just say that they're overlapping and you can't see the second carbon? Like, isn't there a resonance structure where you could? So, like, do we have to represent those when we are drawing these or no?
You're absolutely correct. They are going to freely rotate. And there are two limiting conformations. So this one that we just drew is one of the conformations. And we call this the eclipsed conformation. But you're absolutely right. Eclipse, just like solar eclipse, that word, it means that everybody's lined up. When you see the first carbon, you can't see the second carbon because everybody's strictly lined up. But we know that it's not going to stay that way. The back carbon is going to freely rotate very fast. So once they miss each other, we're going to call that conformation staggered. If they miss each other by 60 degrees, that's the other limiting conformation, which I can draw right here. Have my front carbon, everybody's happy. Top one's black. This one's blue, and this one's red. So let's all imagine the back carbon rotating by 60 degrees. How would I draw this? Where do I even start? Where do I draw this red hydrogen?
Wouldn't it be closer to the
So let's make it clear that this angle is 120 degrees. Right? Because we have all three things attached to it. This is the center, and everybody's apart for the same number of degrees. So that's 120. And now I'm saying that the back carbon is rotating by 60 degrees. Where do we draw this buddy? Do I draw it here?
It would be in between the two hydrogens.
In between which two hydrogens? I have three.
Bottom one.
Yes, you're absolutely right. It would be between the bottom two, right? So anybody has questions regarding this? Am I going too fast? I see some confused faces. So let me explain this slowly. So right here, we're seeing that everybody's lined up. I can't draw them perfectly lined up because I gotta show you that there are things behind. But just imagine that you're only seeing four things. The carbon in the center, hydrogen on top, and the two hydrogens on the bottom. So basically you're seeing what's in the front. And now I'm rotating the back carbon by 60 degrees. And I want you to focus on this red hydrogen on the bottom. So I know that this angle is how many degrees?
120 degrees.
That's 120 degrees. So if I want to rotate by 60 degrees, it would be half of that, right? So I would have to put something right in the middle of these two hydrogens. Therefore, I'm going to put my red hydrogen right here because I'm rotating this way. Makes sense? Or questions?
Why is it 120 instead of 109?
Right, because we're drawing, a Newman projection is a flat picture. So imagine you take a tetrahedron and you smash it flat. Therefore, you end up with a 120 angle. I know by you saying that 109 is that it's, how do I explain this?
Like, that's a bond angle for a tetrahedral, right?
Yes, that's a bond angle for a tetrahedron, but right now we're looking at a 2D picture. It's flat. So imagine you take a tetrahedron and you smack it to flatten it. Therefore, the 109 degree angle is going to expand and become 120 degrees. We're no longer looking at a 3D picture. This is a 2D picture. So let me draw a tetrahedron. So playing. basically, we're looking at this carbon in the center. No, this is not the carbon in the center. We're looking at this carbon in the center. Imagining you're on top of a pyramid. A pyramid is a perfect tetrahedron, right? Okay, so imagine you fly on top of a pyramid and you look down. If you look down on this tetrahedron, what you would see is this. This is the tip of the pyramid, and you would see the 3 little corners of the pyramid, and this angle, instead of being 109, is 120. But I understand what you meant by 109. When it's 3D and you look at this angle, that is your 109 angle. But that angle is different from this angle, which is 120. Should I go over that again, people? It's okay if I need to. I just need to know if I need to.
Yeah.
Okay, let's do this again. Let me erase most of my board because I think stuff is distracting you guys. So, tetrahedron. Okay, so we have a tetrahedron right here. Remember, like, pyramid looks exactly like a tetrahedron. And so if you fly on top of the pyramid, what you would see first is the exact tip of the pyramid. And then you're also going to see all the corners of the pyramid. And this angle that you see right here is going to be 120 instead of 109. Because the 109 angle is going to be, it's hard to see from here, is going to be this one. Got it? Okay, cool. So, I'm glad everybody agreed at this point. So we've talked about eclipsed versus staggered. Let me share my screen again because my drawing is not going to be pretty and the slides are going to look way better than I draw. So we learned about Newman projection, and now let's talk about stability, because I remember just now somebody, sorry I didn't remember your name, somebody just asked me about the stability of molecules, and we're going to talk about that. So this is just a summarization of what I just talked about. These are just nicer pictures that you can look at. I took this picture directly out of the textbook, so you can look at the textbook if you want. So here, what my cursor is on is a staggered picture, which is why we had that pyramid discussion. You know, these angles, the angles between the two adjacent hydrogens is 60 degrees. And we call this angle theta the dihedral angle. Dihedral means two hydrogens. That's why it's called dihedral. And remember that it's called dihedral and its definition because we're going to go into the energy of the molecule and dihedral angles. So when it's staggered, the dihedral angle is 60 degrees. Because if you rotate the back carbon, you rotate it back a little bit, it becomes less than 60 degrees. You rotate it more a little bit, the dihedral angle between the blue H and the black H becomes less than 60 degrees, whereas 60 degrees is the limiting angle. Anybody has questions regarding the limiting angle of the Newman projection? Okay, I'm going to keep going. With the eclipsed picture, your dihedral angle would be 0 because we just talked about how everything's perfectly lined up and you would not be able to see anything in the back. Okay, so which one of these molecules is more energetic? Which is less stable? Can anyone take a guess?
Is the less stable one on the right? The one that's like uneclipsed?
Thank you, Alex. You're absolutely correct. The more eclipsed one is on the right, and I wonder why that is. Can anybody tell me why? Or Alex, can you take a guess?
Is it because the two hydrogens are in the same plane and since they're the same molecule, their forces are being contradicting each other?
Yeah, you're absolutely right. So for people who didn't catch that, we imagine atoms to be little electron clouds. So when everybody's perfectly lined up, those electron clouds are very close to each other and they're going to repel each other. And the molecule is not happy when that happens. Therefore, it becomes less stable. Whereas if we look at the picture on the left, the electron clouds are all staggered. Therefore, they're farther apart from each other and the molecule is less energetic, which is more stable. So this process happens very naturally, and here's a representation of the potential energy of the molecule. I strongly suggest that you review this picture after the class. Since you will have everything available to you for the exam, I'm not too worried about you memorizing it, but I want you to understand what the peaks and the inverse peaks mean. So let's quickly go through this. I want you guys to all focus on the pink hydrogen and the blue hydrogen. So if we start from the beginning, just as Alex suggested, the molecule is at its most energetic state. We start from 0 because see the dihedral angle here is 0 degrees. So as we rotate clockwise, we rotate by 60 degrees. It becomes staggered. That's the other limiting conformation, and the molecule is at its least energetic state, which is why we see it here. And we keep rotating the molecule. Now the red hydrogen keeps going down, and it overlaps with the black hydrogen over here. Everybody becomes eclipsed again, hence the peak. Anybody has any questions regarding how this graph works?
I have a question on how does energy relate to stability? Why does more energy make it less stable?
Right. That's a very good question. Let me think about how to answer that. Imagine a four-legged furry animal, and you have this little animal chilling on its own, and you're like, I want you to pose for me because I want to take a picture. I want to post it on Instagram. So you start fiddling with your four-legged animal. You fiddle with your little dog, and you want your dog to face you, but you want your dog's body to, be horizontal. So the dog would have to be very strained in order to pose that pose for you. Do you think the dog will be very happy doing that? Dog wouldn't be happy, right? Because that's uncomfortable. So the dog will feel very agitated, and he or she will want to go back to its original form where everything's apart from each other and, where he's happy. So this is the same thing. If your molecule's natural state is to be as far apart from each other as possible, all the atoms, but you say, no, I want to twist you. I want everything to line up. Well, okay, you imagine you twist it, everything's lined up. What do you think is going to happen once you let go of it? It's going to twist right back. Everybody's going to be staggered again. Therefore, when you twist it, you give it energy, and its potential energy will go up. But once you let go of it, it's going to release all the energy that you give to it. Therefore, we go down to the bottom of the peak. Cool? All right. So, study this graph on your own, and it seems like nobody has more questions regarding this picture, so I'm just going to move forward. I don't know if you've all seen this meme, the slap a chicken meme. So I'll give you 2 minutes to read the meme. If kinetic energy is converted to thermal energy, how hard would I have to slap a chicken to completely cook it? So it's a physics question. I encountered this meme, and I started doing weird calculations about everything. And remember in the picture that we just saw, the energy difference between the top of the peak and the bottom of the peak is 2.9 kilocalories per mole. The hell does that mean, right? I'm pretty sure very few people knows how much energy that is, since you haven't studied organic chemistry for that long. So I did some weird calculation. Let's talk about 2.9 kcal per mole. How much ethane is 1 mole of ethane? Well, we take ethane at room temperature. We know from Gen Chem that room temperature 1 mole of gas takes up 22.4 liters of space. So that much space is a third of an SUV gas tank. So to do something to a third of an SUV gas tank worth of ethane, we need 2.9 kcal per mole. And that's about the energy of burning 1 French fry. So this simultaneously causes 60-degree internal rotation of that much ethane molecules. You have to burn 1 French fry. And to put things into perspective, the ethane CC carbon-carbon single bond energy is 90 kcal per mole, which is about 30 French fries. So if you want to break a mole of ethane single carbon bond, you need about as much energy as what's released from burning 30 French fries. So that's plenty of energy. The carbon-carbon single bond is actually very, very strong. So that's putting things into perspective for you. Any questions regarding the calculation that I just did? Nope? Okay. So, last thing. Seriously, above 0 degree Kelvin, molecules have random motions. That's what we learned in Gen Chem, right? At 0 degree Kelvin, everybody's absolutely still. There is no energy. Thermodynamics comes to a standstill. But as soon as you go above 0 degree Kelvin, everybody starts to move randomly. Everything's by chance. So everybody's going to bump into everybody. Random collisions happen, and it results in energy transfer. Some of that energy will transfer into the wall the molecule bumps into. Some of the energy will get lost as heat energy, but a little bit of that energy is going to get transferred from atom to atom, molecule to molecule. So our internal rotation is caused by the absorption of that kind of energy transferred. So question, internal rotation is more or less probable at higher temperature? I'm just going to wait until somebody starts to talk to me.
More.
It's going to be more probable. Why? May I ask?
Because internal rotation requires energy, and the higher the temperature, the more the energy of the kinetic molecules in, in the molecule, and so the more energy it has to spare in order to rotate.
Yeah, you're absolutely right. Thank you for the answer. I think it's perfect. I could have said it better. So, to sum up what she just said, with higher temperature, we have more thermal energy, which can turn into more kinetic energy, which results in bigger energy transfer between the molecules that collide with each other. Then it will be more probable for our internal rotation to occur. Questions regarding what I just said? Nope. Okay, I'm going to stop sharing this. How do I stop? Yep, here's how I stop. So I booked this class to be 1.5 hours long because I thought, sometimes I might end before 1.5 hours. Sometimes I might just, stop at 90 minutes. There's one more thing I would like to talk to you guys about because it's very important and you will definitely be required to know it for your actual organic chemistry course. And also, it would be unfair for me to not teach it. So, we just learned about how to convert a molecule to its Newman projection. What about converting it backwards from Newman projection to a skeleton drawing? Anybody know how to do that at the moment? If people know how to do that, I'm just going to let go. How comfortable is everybody with skeleton structure drawing?
Still practicing, so not very good.
Still practicing. That's okay. That's okay. As long as you know what it means, you'll be fine with the exercise we're going to do very soon. So, one more exercise before I let you all go have lunch or enjoy the rest of your day. We're going to convert a staggered Newman projection to its skeletal drawing. And this Newman projection I'm going to draw is going to look a little bit more complicated than the ethane one we're going to draw because the ethane gives the most simple Newman projection of all. So, I want you to start drawing with me. I have my giant carbon molecule. And I have CH3. H. I'm going to draw CH2, CH3, CH3, CH2, CH3, H. Everybody following what I'm drawing? Cool. So, what do we do when we encounter a question like this? I can break it down to 3 steps. So, for simple alkanes, we're going to use these 3 steps to turn a Newman projection into a skeletal structure. So, the first step is to draw a 2D picture of the carbon chain. 2D drawing of carbon chain. How do I convert this into 2D drawing of a carbon chain? I'm going to tackle one carbon at a time. I know that by drawing a Newman projection, I'm looking at a carbon-carbon single bond. So the first giant circle has to be my first carbon. Right? So I'm going to draw my first carbon. What do I do next?
You connect it to another carbon.
I connect it to another carbon. Which direction do you want me to go?
To the right.
You want me to go to the right?
Yeah.
Which carbon is this?
The back carbon?
The back carbon. Thank you, Alex.
Okay, yeah, thanks.
Yeah, I mean, you were not wrong. It's the back carbon. We have to draw it at one point. So let's focus on the first carbon, right? We're going to draw the back carbon when we get to it. So first carbon, what do we have attached to the first carbon? Okay, we have CH3, CH2, CH3, and H. So we're just drawing the carbon chain. We're going to ignore the H. It's not part of our deal right now. So what should I add to this carbon?
CH3.
We're going to add a CH3. That is very good. We're going to add a CH3. I'm going to add it anywhere because I don't really care. So CH3. So because I am drawing a carbon chain, I'm not bothering with all the hydrogens. I'm just going to add a C, the methyl carbon here. What else do I add?
CH2, CH3.
CH2, CH3. So CH2, another C, CH3, another C. So done with this part of my carbon chain. We're done with the first carbon. What about the second carbon? What do we have attached to it? We have CH3, H, CH2, CH3. The same thing, right? So what do you want me to draw here?
A C.
A C. Okay. What else?
And then the C attached to the central C, and then that C is attached to another C.
You're absolutely right. So we have a methyl, which I drew here, and an ethyl, which has two carbons. Oh, sorry, the methyl is here. We're looking at the back carbon. The methyl here and the ethyl here. So ethyl has two carbons. I'm going to add two carbons. So now I've completed my carbon skeleton. Any questions regarding this, or should I go over it again, or color code it so that it becomes clear?
Can you go over it again, please?
I'm sorry?
Can you go over it again, please?
Absolutely. So I'm going to color code stuff, actually. I think that's gonna, where is my, keep all my shit in the same place. Okay, so erase all the carbons. Don't want to bother. Let me color the carbons on the first carbon blue. So, first carbon, we have CH3, CH2, CH3, and H. I want to add both of these groups onto this carbon. So I'm going to add one C, which stands for CH3. I'm going to add two more C's, which will stand for CH2, CH3. So I can add it on top or add it on the bottom. It really doesn't matter because I have more space on the bottom. I'm just going to draw this. We good for now? Everybody clear? Okay, great. We're done with our first carbon, right? The blue carbons. Now I'm going to move on to color the back carbons red. So we have CH3, CH2, CH3, and an H. With H, we're just not going to look at it. And we have a methyl and an ethyl. I want to add to the second carbon. So I'm going to add a methyl. I want to make it perfectly symmetrical, but you don't have to. I just want to draw it symmetrically. So we have this CH3, and here we have two carbons. So I'm going to draw a carbon and another carbon. And now we're done. Make sense?
Why did the C in there's two black C's in the middle. Where did they?
Right. That's a very important question. Remember here, the big giant center is a carbon atom. We're looking directly at that carbon-carbon bond.
Yeah.
That's why we start with this carbon-carbon bond.
So it's two carbon?
Yes, because remember when we drew the Newman projection for the ethane molecule, we have one carbon in the front, one carbon in the back, and you can only see the carbon in the front because everybody's eclipsed. Now we have a staggered picture. But when you look directly at that carbon-carbon bond, you cannot see the other carbon in the back.
Okay, that makes sense.
Make sense? Okay, cool. So, we're done with the first step. Everybody good here? Let's move on to the second step, which is super simple. Cannot be easier. We're going to add all the hydrogens. So each carbon has to have 4 bonds. So just look at your carbon and add hydrogens. If your carbon already has 2 bonds, you add 2 hydrogens. If your carbon has only 1 bond, you add 3 hydrogens. And if your carbon has 3 bonds, which we don't have here, you just add 1 hydrogen. Which we actually do have. I take that back. Our first carbon has 1 hydrogen attached to it. So what you will end up having is this. Same answer as I do. Everybody agrees? Okay, wonderful. So now we have our 2D picture of this molecule. And we're just one step away from our final answer, which is a skeleton structure. So for a skeleton structure, we know that for the alkanes, we have to draw zigzagging bonds. And for each carbon, we have a turning point, and we just neglect all of the hydrogens because we just assume that they're hydrogens. So how do I do that? First thing I'm going to do is to number all my carbons. I'm going to number my carbons with the right pen. So, find my carbon chain. 1 carbon, 2 carbons, 3 carbons, 4 carbons. And I have 2 side chains, so I'm just going to number them as well. 1, 2, 3, 4, 5, 6, 7, 8. It doesn't matter how you number them. You can number them however you want, as long as you keep track of how many carbons you have, because it's very easy for you to lose carbons when you convert a 2D picture to a skeletal drawing. So, we have these. Now I'm going to start drawing my skeletal structure. My main chain is a 4 carbon chain. I have 1, 2, 3, 4, 4 carbons just going this way horizontally. So I'm going to draw my main chain first. You can see everything. There is so much light. Okay, so 1, 2, 3, 4. I'm going to number my carbons. 1, 2, 3, 4. Done with my main chain. And now I'm going to worry about my side chain. So I'm going to look at my second carbon first, because it comes first. I have carbon 5 and 6 attached to carbon 2. So what do I do with that? I'm going to my carbon 2. I have 2 carbons attached to it. So I'm going to draw 1 carbon and 2 carbons. And I label them as carbon 5 and carbon 6. What do I do with my carbon 3? I see 2 carbons attached to carbon 3, which are carbon 7 and carbon 8. So I count. 1, 2, 3, that's my carbon 3. And I have carbon 7 and carbon 8 attached to my carbon 3. And there it is. That's my skeletal drawing.
Does it matter which way you draw, like the angle, like the lines, or as long as you just draw it anywhere?
As long as you draw the connectivity correctly. As long as your carbon 2 has 2 things on it, your carbon 3 has 2 things on it, doesn't matter how you turn the picture. It will be fun. Questions regarding how I go from here to here, or regarding any steps that we just went through?
For the main chain, is it supposed to be the longest carbon chain?
You're absolutely correct. When we name the alkane, our main chain has to be the longest chain. Whereas with the drawing, you can name the carbons however you want. So our main chain, if we were naming this alkane, we would have to go from here. Our longest chain is this one. I'm going to write over it with my black cane. That's my longest chain when we're naming it. But since we're not naming it, you can number the carbons however you want, as long as you go from this to that. And once you're done with drawing, you can find your longest chain and start naming it. Make sense?
Thank you.
Oh, you're welcome. Any more questions regarding what I just did?
How do you name it?
That, you're going to have to look at the slides that I will upload in just 5 minutes.
Okay.
Yeah, it's very straightforward. It's strictly from a textbook. Okay, any more questions, comments, concerns? I was going too fast, too slow, too nonsensical, stuff like that.
Yeah, I think for the homework there was staggered and eclipse, but that was a gosh, I don't know how you say it. Yeah. So how would we do that one? I don't know, yeah.
I haven't seen the homework problems. Sorry, I don't know what you're exactly referring to because I didn't write the homeworks. But if you have time after this, you can stay here and I will look at the homework and answer your question.
Okay.
For the rest of you who don't have questions regarding that matter, you can just feel free to enjoy your day. I'm done with my lecturing for now, and I will see you next Wednesday. And feel free to stay if you have questions, and if you don't, goodbye.
Thank you.
You're very welcome.